Well, I think we're about there. Welcome back, everyone. For today's class, we're just moving through this section 7.2. This was a rather large section, so we may not finish it this week. We'll adjust the due date as normal so that it's going to be due, looks like probably more likely April 15th will be the due date. We'll complete this one on the 8th. At the moment, pretty much what we're doing in the course after moving through the proof sections, chapters 4 and chapters 5, it's really just working on applications. We're following the syllabus with the chapters that are indicated, just picking up as many applications as possible. We're not going to try to rush through everything to try to cram it all in at the end. We'll be working at about the same pace towards the very last part of the course. But before we get started today, any questions or comments to begin, folks? Okay, let's get started then. So in section 7.2, it's organized in really three big chunks. The first chunk was all about divisibility properties that we got through. The next chunk is going to be the division algorithm, or the so-called division theorem is our way our author likes to call it. And then finally, we get into the namesake, the modular arithmetic chunk. So we're essentially in the middle of this section at the moment. And here's exactly where we're at. Again, this kind of hurts my head a little bit because this theorem is really famous. It's in a lot of algebra textbooks. It's almost universally called the division algorithm. So that's a little bit strange choice, but it's the right choice our author made because the reason he doesn't want to use algorithm right here is because this is a course about algorithms, and he wants to think of this as being the division actual algorithm referring to pseudocode. So if that seems weird to your head as well, then sorry about that. We'll call it the division theorem. If I slip up and call it the division algorithm, still referring to this one here. Also, I'm reminded by that red text there. There is a edit, a revision on these notes here in 7.2, as well as the one in the Blink lecture notes has a revision as well on 7.2. The revision was that part is supposed to be less than or equals to. And I copied less than or equals to on this one, but that is not true. This has to be strictly less than k. So this is the whole theorem. It says let k be positive, greater than or equal to 1. Let n be any integer. It just says it's an integer. Then there exists integers d and r. Moreover, they are unique integers. There's only one way to solve this problem. There are unique integers g and r such that r is going to be between 0 and k. K came from here. And k times d plus r is n. N came from over here. And that's the whole theorem. Really weird theorem when you look at it. It's formatted in a way that makes it vague what's even being communicated. Why is this called a division theorem? You might be asking yourself the minute you see this theorem. But here's one way to think about it. I like the other title the author gives us. This is a theorem about really floors and remainders. So let's try to track those concepts through. Maybe starting with remainders. This is the thing we're more familiar with, I would say, thanks to modular arithmetic we have been doing. When we talk about the remainder, we're talking about r, and we're talking about that quantity right there, the quantity that could be 0, but is strictly less than k, and it's also an integer as well. So if that's the case, we have a lot to say about r. The r highlighted right here, the remainder, is r equals, actually, let's write it this way. Let's go n mod k equals r. So that's what our r is. But on the other hand, we also know that n mod k, this is a formula supplied by our author that has gotten some use, especially when we do modular arithmetic with n being negative, for example. Formula goes n minus k times the floor of n divided by k equals r. And let me fix just a bit of color coding right here. Floor of n divided by k. I notice curiously, The notation for n and k has been chosen really very well in this section because it's matching up with everything that we've been writing down all along, after the corrections, of course, that we see here in the violet color. So we're always thinking about n divided by k in this structure. So this is a division theorem, and finally, division shows up right there. The floor of n divided by k, that's the floor function coming up in this theorem. So we have a remainder, we use the modular arithmetic in this expression to indicate it, the remainder after division of n by k. This formula right here also computes n mod k, still the remainder. And that's the floor right there. Let's take a look at this equation next. Now just try to tie all this together. So we have kd plus r equals n. From this equation, we could say that n divided by k, recall that's pretty much what these problems are all about in this section. N divided by k would be equal to d plus r divided by k. So if we do that kind of division, we get this output out. R, so once again, the remainder, k is what we're dividing into, and d is going to be the result upon division. That's in fact, the floor function right over here. So the floor shows up, the remainder shows up, it equals n in property 2, but this is the different view. If you're thinking about division, and you want to really fit a mental picture of division in this problem, take this whole entire equation, divide it by k, and this is just another way to express the same equivalent information. So n divided by k is going to go in d times with the remainder r, but k still will divide r. Makes sense why r has to be strictly less than k. If it was equal to k right here, that would just be a +1. There's no reason to write r divided by k. So that was an important correction to make. So there's the tie-in. We have a formula from way back in chapter 2, but it's good to know what was this saying and how does it tie into floors and remainders. Any questions at all, folks, looking into the division theorem a second way? Okay, and this is a great way to read this kind of technical information, whether it's called a theorem, whether it's called an algorithm. Try to break it down related to things that you're familiar with. See how the concepts of floor and remainder might actually track through the statement, because he would not have called, our author rather, would not have named theorem 4.1, floor and remainder, if there wasn't a tie-in on both of those concepts simultaneously. So best way to read this theorem is force in the tie-in as you go. So next, we'll just practice using this division theorem. We'll compute 248 mod 15. Then back over here, we're going to redefine k as 15 and as 248. Same stuff we see right here, but then fit it back into the division theorem. So this is just an example of helping us work with that theorem, getting it in our mind. Let's start off with 248 mod 15. And maybe before we get too far, when we look into this and we see we have a k value and an n value, and we're plugging it back into the theorem, it might not be a bad idea to write some extra information even above this. 248 mod 15 is really just asking us to do n mod k. So I've assigned n248, k15, and we'll keep that tracked through our mind as we run through this whole problem. So do 248 mod 15. Loads of ways to do this kind of problem right here. You might imagine, well, 15 multiples, take a whole bunch of multiples of 15 and get to the point where you're just about to go beyond 248. The remainder quantity is r, n mod k. Or if this just feels like it's a lot of mental work, we'll use this structure, which does feel like a cop-out because note, I'm going to actually divide here when the point is to do the division over here in a certain sense, but just a clean way to actually implement this mod. So this will be equal to 248 minus 15 multiplied by the floor of 248 15s. So this will be 248 minus 15 times some quantity over here. Let's grab a fast calculator. So 248 division by 15 gives us 16.5 repeating. That means the floor of that quantity right here is just 16. So drop in the 16 into this location. It tells us if you subtract 15 16 times, then you will not force this negative. You'll get a number between 0 and k, which is 15, and that's the remainder r. So let's do this last subtraction, 248 minus 15 by 16. Gives us 8. And that's the r value now. This was the floor value, but this was a better one to look at. It came out at exactly 16. So this is the part that's D in the theorem, and this is the part that's R in the above theorem. We did it, folks. This is a problem that we could have done in an example, or excuse me, in chapter 2, all the way back at the start of the course. But now it feels a little bit different because we're trying to tie it together with this theorem right above. Any questions at all with part A? Okay, I answered part A in kind of a weird way because it sort of answered part B as well. It said find the unique integers R and D, satisfying theorem 7.1, and I just pointed at them right here. But let's do part B anyways. Let's also check that we have the right answer at the same time. So if we're supplied values, k is 15 and is 248, what we're really doing is, like we mentioned above, n mod k, which is really now this time 248. Mod 15, it resulted in a value 8, which is R. And if you didn't do this formula right here, you would still want to calculate the floor, which is going to be floor of 248/15 coming out of 16. And that's the part D right here in the theorem. So to see if we really got this out right, let me use this part. Now, n has to be equal to kd plus r. We have the n values, we have the k values, we have the d value and the r value. So plugging that all in, let's see if our last equation checks is true. If it's false, we need to do some backtracking and see where the error could be. So n is 248 equals k, that's 15, times the floor of 248/15, that was 16. Then plus the remainder after dividing 248 by 15, that remainder was 8. Let's check this out. 248 plus, or excuse me, not that 15 times 16 plus 8 does in fact give us the 248. So we've got the right values. We did a division in a pretty weird way with modular arithmetic through a formula, and then we tied it back into what this theorem is saying. If you do n divided by k, with those two specific values, all this was saying is d is 16, r is 8. Weird way to say it though, right? It's really saying a little bit more, but that's our first run through that kind of information. Well, any questions, folks? Solving up to part B. Okay, I think these problems are kind of fun because, again, all we're doing is dividing, but there are so many little concepts that go around with this. So let's try this out again. This is the one problem that had that side comment we mentioned before. I think this was a great question. I'm glad it was assigned. I mean, we were definitely going to assign something with a negative number mod something else. But the fact that this one question got so much engagement really shows that there's a lot going on. The author really wrote this book well by dumping in that question there, which we could kind of resolve in some roundabout way. But what truly had to be resolved through this theorem, I think this is the best tool to understand what is going on with negative 42 mod 17. So let's do this all over again, see how it goes. First things first, it says compute negative 42 mod 15, but let's think of that as being n. So n is negative 42. Totally allowed. There was never anything here that said n couldn't be negative. So it's n mod k. This is just us defining k at 17 by the correspondence. So let's run through that. Negative 42 mod 17. This is one where I would definitely want to use the formula. It's confusing enough as a process all on its own. So let's go negative 42 is the n. Minus k means minus 17 times the floor of n divided by k. So that'll be negative 42 divided by 17ths. This now becomes negative 42 minus 17 times. Now we need to do a floor computation. The negative does carry in this location, so it's negative 42 17ths. And this is always a little pretty tricky. We mentioned that before. The floor of negative 2.47 is negative 3. Sometimes it might help writing down a number line to really see it. But does that make sense to everyone that floor here becomes negative 3 based off that integer? Or excuse me, that decimal number? Okay, let's drop it in. Negative 3 goes into that location. And then finally, let's run through the computation of negative 42 minus 17 times negative 3. Notice it's forced 9 positive. Seems kind of weird, but that's the guarantee in part 1 right here. In the division theorem, the remainder after division by k is going to be a number strictly constrained between 0, so non-negative, and less than k, so it had to have been less than 17. That number is 9. Really pretty weird. That's the number that we got in the homework assignment. But now we get to do the good work in part B of clarifying what did this mean exactly. That's just the unique number. Remember, there is only one way to solve this. There's a unique number, and it's positive 9 to the problem of negative 42 mod 17. Really, really strange. But let's tie this together. That's the floor. When we say floor and remainders on this name of the theorem, floor is negative 3. When we say remainder, we mean the outputs to negative 42 mod 17, the value 9. Next, we'll put it together in part B to see how those values highlighted really work out for the integers R and D. Any questions first, folks, on our solution to part A? Okay, let's write this out then. So I'm going to think in terms of this equation again, like before. I'm going to write in n equals KD plus R. That's just from the formula. Plug in the values we actually have from up here. So now negative 42 equals K, which is 17, times D, the floor of negative 42 17ths, that's negative 3, plus R, that was calculated over here, so R is 9. And let me reformat this a slightly different way. I'm noticing that as I write this down, the way I'm answering this question is more performing a check. Let's also answer it a little bit more definitively by just simply saying R is 9, D is negative 3, just so that we were really saying it someplace. We said it here, but that's kind of a vague way to say it through an equation. So let's check out if this really works before we get too far along. We're checking this equation here, 17 times negative 3 plus 9. Sure enough, it really is negative 42. So that tells us if we think of this mod process as fitting into the division theorem, and because there's only a unique way to find R, one and only way, we're forced into the conclusion, negative 42 mod 17 equals 9 itself. Only because that's the only way to make this equation right here really work out. So that's another look at what's going on with modular arithmetic with negative mixed in. But if you're kind of like me, this example might not have been the end-all be-all explanation. You have to go even further and develop an algorithm and see if that algorithm is even making sense. In the process of working with that algorithm, it can explain what's really going on with modular arithmetic. We had a negative 42, here it is, and we were dividing by k, which is 17. It's over here, that's 17. In negative 42 mod 17, we think of the remainder upon division. But what we are actually doing is taking that 17 and multiplying it by the right negative constant so that we get a number plus 9, equating us back to negative 42. And that's all it is, the right number of shifts through the floor, adding the right remainder to get us back to the right end value. Strange process, but let's implement it next as an algorithm to get a better intuition on it. First, any last questions or comments at all, folks, on example 4? Okay, so next, we're going to look at what our author would call the actual division algorithm more likely. Rather, it's just listed as a bit of pseudocode. Here it is. I have the theorem above because the pseudocode is attempting to implement the information in the theorem down into the statement here. And what we want to do is trace through the execution of this pseudocode to see just how it's working. And by doing that, we get a better understanding of what is even going on with the floor's remainder, the division theorem, and modular arithmetic. But you know, when I look at this, I didn't realize something the first time I typed up these notes. I only realized that this morning when I was proofreading my notes. This is great syntax. It does a wonderful job, but it leaves off something. Here, n could be any integer. We just literally did one with n negative. Whereas here, this pseudocode has n strictly greater than or equal to 0. I think maybe before we even do example 5, let's extend this pseudocode so that we can have a division algorithm that handles any integer n whatsoever. That way we could verify it on this one, see if it's working out, and we'll also verify it on this one, the more ordinary problem. So let's do that next. Let's extend this. Let's maybe kind of go like this, just take a screenshot. Or this is a copy paste this time. We'll come back to the trace problem, example 5 below. This is a homework example or a homework problem assigned as well for different values, so we definitely want to do that one. But let's extend now this algorithm to a full-on division algorithm. So that's going to be our goal. Extend this so that it handles n less than 0 as well. First, let's take a look into what it's even doing in the first place. So it says, take a non-negative integer, k greater than or equal to 1. That's nice. That matches up with the theorem. So I like that part of the algorithm. We're going to output n mod k and the floor of n over k. That makes sense because this is floors and remainders. It should return a floor. The floor that we're returning is d, and that's this part of the algorithm right here. It'll return d to us some way, somehow. We'll see how it executes. It's also a theorem about remainders, and remainders enters the picture right here, n mod k, and the fact it's going to return r itself down below. But how does it start? It starts by setting r equal to n, d equal to 0. While r is greater than or equal to k, that's if, say, hang on, let me think about this. Yeah, that's if n is, or excuse me, if r is greater than or equal to k, let's imagine maybe n is 30, k is 5, something along those lines. What we do is we subtract k. Let's think about that. So if n is 30, and k is 5, recall this problem is really about n divided by k. So we would go and do this division, 30 divided by 5. Let's imagine this is a pretty hard process, maybe just nasty numbers, something along those lines. How would we divide? Well, you could divide by subtraction. That's the brilliant idea in this pseudocode right here. We're not going to do something really taxing to the poor silicone on the system. We're just going to do something where we subtract. So we might go 30 minus 5 for a 25, set d equals to 1. That's the d incrementing to d plus 1 on this line of pseudocode. Notice we're tracking what happens to d every time we run through this. Now, if r is still greater than or equal to k, this is the new r value, 25, still bigger than 5, you just do this again, subtract 5. You'll have 25 minus 5 to get 20. You've subtracted twice, so now d increments to 2. And this keeps on going until you're at 10 minus 5 equals 5. D is going to be equal to 5. And you do it just one more time because that's the new value for r right here. R is now equal to k, 5. We run through it once more and we get 5 minus 5 equals 0. D is set to 6. Well, this won't run anymore because no longer is r greater than or equal to k. It's set to 0 on this step. So at that step, we're just going to skip across the while block, return both r and d. R would be returned as a 0. Makes sense. That goes in evenly. Remainder is 0. And d is going to be returned as a 6. Also makes sense. That's how many times 5 goes into 30. So that's the idea of what all this is trying to say. But now our goal is to extend it further. Any questions at the moment about the first part of the algorithm itself? Okay, I'm going to erase some of the scratch work here so it's not as much of a distraction as we go forward. And now let's do the extension. I'll write out the pseudocode in the same style that the author did over here. I'll recall it mod and div. I think underscore would work better for most systems, so let me do it with an underscore. Mod and div is going to accept 2 inputs this time, n and k. So our pseudocode is starting to get a little bit more built up as we go. I think this is our first 2 input function that we're building up. So this will be defined as, let's see, copying the same structure for the pseudocode. Let's say what our input should be. Input integers n and k greater than or equal to 1. No error checking here, just what we intend to do with this. We could do error checking if we had a lot of extra time. We really want to polish this. But now this is matching up the theorem, and it's just an integer, allowed negative, k greater than or equal to 1. Now, first thing we'll do is, let's see here. We want to handle a new case and negative. So maybe what we should do just first and foremost is maybe do an if-else structure. Let's go if. Let's make this be the positive case. N greater than or equal to 0. We'll do this block right here. So essentially, we're just plagiarizing this bit. This is going to work terrific. We don't have to reinvent it whatsoever. So if n is bigger than or equal to 0, maybe even before that, that line right here is actually pretty important. Whether we're dealing with case positive n or negative n, we must initialize r and n to those values. So let's make sure that happens at some stage. I'll write it as r defined to be or set equal to n, maybe on another line down here, k, or excuse me, d, defined to be 0. Now, if n is greater than or equal to 0, we run this part right here, 2, 3, 4. So we'll set R is going to be R minus K, that division by subtraction example that we were looking at earlier. Then set next, D is D plus 1. Then that completes the if section. The little curly brace there. Now we want to run off to the negative section. So this is the else part. Let me see if I can sneak in just a bit of space. There we go. Else. We don't need to write a condition. This will just be strictly now for negative values of n. So what do we do if n is negative? Essentially the opposite thing. We set R defined to be R plus K. We start adding values. So when we were looking at this one right here with negative 42 mod 17, we start adding 17 to negative 42. We added it 3 different times. Well, that negative there gives us that adding. So there's the negative 17 and there's the negative 3. So we added 17 to negative 42 3 different times until we got in the range between 0 and K was 17. That value was 9, and we couldn't add 17 any longer. We would be beyond K. So in this situation, due to the double negation we see right here, we're just adding. So we change the syntax from minus K to plus K. Kind of cool in a way. So one small change here to here. Second change is we do a minus on this one. So D is set equal to D minus 1. So change this to that. Let's see here. Hang on, let me see. Let me think about this. I think I forgot one big part. The while, that never got written in, did it? I initialized, let's see, well, R greater than or equal K. I set the values, but the while should go right after the if. So if n is positive, while R remains greater than or equal to K, we'll do the syntax down below. So let me insert a while here. While R greater than or equal to K, do these structures, and then stop the moment this condition fails. We have to stop because if the condition fails, and we did it again, we would exceed that range, go beyond K. And another while should happen right here. But what should it be? This should be while R greater than or equal to K as well. So this should do the job for us. Supposedly, this is borrowing from the author's supplied pseudocode, now extending it with an if and else structure to handle negative n now. Well, the only way to really know if this was going to run and really give us the values, like on examples 4 and 3 that we just did, is to next implement this into your language of choice, see how it runs. But any questions at all, folks, with this full structure here? Okay, this is the moment of truth. Let's see how this is going to do for us. We'll call this, why not, mod and div, because that's exactly what it does. It's a pretty brilliant name. Mod and div. In this particular language, what we do is we add a new structure. Left arrow is kind of like the colon equals. It's an assignment. We're going to assign into that container a function which will contain these inputs. So 2 arguments to this function, n and k. So everything constrained between these curly braces here and the one highlighted is going to be our actual function itself. Let's start writing this in. Now, what should we do next? Well, we don't need to write in this part at all. This looks like it feels more like a comment, but we kind of captured it in spirit when we said that. That's telling us those are the inputs. We need to do the initializing. So let's set and initialize R gets n, D gets 0. So that's the initializing phase of this. Next, it's going to be the if-else structure. So if n greater than or equal to 0, we will do something while r is greater than or equal to k. I'm starting to get kind of convoluted, but let's see if we can get this in cleanly. While r greater than or equal to k, and I always kind of debate myself if I want more curly braces here. It starts to get a little bit stacked, but in a good IDE program, it really helps with seeing the structure of what is going where each time you click on one of those braces. So more might not be bad. Let's see how it runs. So while r is greater than or equal to k, we do two different things. We set r to r, decreased by k, and we increment d by 1. So d gets d, add 1. So those are the new values for r and d. It just runs until r exceeds k. Well, if we only pass positive values, that should do the job for us. Maybe before we get too excited about our success on this, let's see if just this part runs, and then we can try it out. Not on that example, or yes, not on this example, it won't work. Let's try it out on this example right here. So I'm hitting Control A, Control Enter to run all the syntax. We should have a new function called mod_mdiv. There it is. We have a mod_mdiv function now defined in the environment. And to see if this actually runs as intended, let's call mod and div, pass to it. Let's see, it's got to be n and k. Thankfully, that's n mod k. So 248, 15. Nothing happened. Well, something did happen, right? But notice I never told the function to give me an output. Let's fix that right here. We want to return. Let's see, we're returning first. If this is mod and div, we should return r first, or we're going to confuse the users of this. And then we should return d. Okay, let's see how that did for us. Really bad. It tells us multi-argument returns are not permitted. That's a lie. This is just a syntax error. I didn't like the way I put those together. So let's put in a new structure. This is just a nuance of this language. Combine r and d as one single vector. That should work for us. Mod and div 24815 is just redoing this whole problem right here. And it gives us 8, that's the modulus part. 16, that's the floor part. So it did it for us. It, in fact, gives us the floor and remainder, but only for positive. If we try to run this on -42 mod 17, let's in fact do that. We get -42, 0. Well, the syntax just stops right at this one. It has nothing to do because, let's see, this never ran. All we did was initialize values and then return them right back. This condition never got hit. So we need to extend our pseudocode a little bit further and implement the last part of this structure here. Maybe before doing that, let's also fix it. I'm only just now noticing when we stare at all this pseudocode does a whole lot of work and then gives the user nothing. Let's return some values to it. So let's say return. How did our author say it? Just that way. I'll try to copy the structure. Return r, comma, d. And in actual language, we had to say it this way. And if it's Python or C++ and so on, lots of different ways to implement this. But this is the value of good, nicely written pseudocode. We can take whatever this is and just contortionistically change it into the right structure based on your language of choice. So now let's go over here. We're extending this now a little bit further to the else condition. So here's the if, here's the else now. I don't want to forget the while again. So else, but while r greater than or equal to k, we'll do these operations. R gets redefined as R plus K this time. And D gets defined as D minus 1. And just to copy that structure, let me include this wraparound. Okay, so hopefully everything has got the right delimiters here. Let's double check. So that one corresponds to the else. That one corresponds to the if. I think we're in business. This should run. So let me hit Control A, Control Enter. Let's test it out on a value that we know works out well. There's 816 again. And now let's test it out on a value like this right here, negative 42 mod K. That would mean N is negative 42, K is 17. When we go to pass this into the function, and it spits out, not what I was hoping it would spit out. Something's gone wrong. Same as before, it looks like my if ran on this, the else did not. Huh. There's got to be a problem with our code somewhere. Let's take a really close look at this. And we'll see where the trouble could be. Running it again out of paranoia, that almost never works when you're trying to debug something. Yeah, some problem here somewhere. We have R minus K, D plus 1, R plus K, D minus 1. I'm thinking the trouble is if R is initialized to N and we pass a negative 42 and it's spitting out negative 42 and spitting out 0, it's telling us neither one of those structures even ran in the first place. Something really strange going on with this. Let me try one more time with that one. Yeah, that still looks correct. But something in this structure here is just not quite working out right. I do have a cheat sheet. Let me consult my cheat sheet here. I think I see the problem. Should have said, well, R is less than 0. Let's take a look at that. Rerun this one. And hey, I think that's right. Let's take another look. We should have been given a 9, that's the value of the mod, and a negative 3, that's the value of the floor. So that did run correctly as per this example. Negative 42 mod 17 gives us 9 and a little bit more. Let's take another look into that. The pseudocode had an error right exactly here. The fix was, I was just blindly copying the structure, R greater than or equal to K. But if N is negative, R itself is going to be negative when we start this out. It's initialized negative, right? When we threw in negative 42, R itself became negative 42. And so this condition doesn't even really make sense. We should have said, while R is negative, we're trying to force that value into the positive range by repeatedly adding on values of D using double negation in the equations we saw above. So that was the fix right there. And now we have a pretty interesting function. It'll do modular arithmetic for us. It's annoying because it gives you the actual division portion as well. But in this particular syntax, and in many other languages, essentially every other language, if you have multi-outputs, there's a way to subset into this. Bracket 1 is just saying, give me the first value. Run that, and now mod and div with bracket 1 is only giving you the modulus every single time. If you wanted the floor, you would just go 2 to get the second output, negative 3. So it's kind of nice. We have implemented mod and div as just another way to explain what in the world is going on with negative 42 mod 17. So this is another take. All you're really doing is this process. You're coming in from the opposite direction of thinking of division by subtraction, but now reversing the entire method. Well, any last questions, folks, on getting through this algorithm here? Okay, so now we have a theorem, the division theorem, but this entire theorem has been implemented as a nice algorithm. Well, we would possibly want to really prove that this implements what we want to do exactly, but we're going to hope that that is, in fact, the right algorithm. Worry less about proving it in this section. Coming down below, this problem is really more about just tracing through the execution of mod and div. I felt like the problem with negative 42 mod 17 was such an interesting one. It was a good idea to just implement the entire pseudocode for all cases like this. So this is just another look into what exactly this pseudocode is actually doing. Again, it's a homework problem and it's a slightly tedious one. I made the number here a little bit smaller and the number here a little bit bigger to make it feel less tedious. But while we're doing this, and because of the tedium, let's actually bump this one up a little bit. Let's make this a classroom edit and make it a 18. That way we won't feel like we're literally a robot running through this for so long, doing the trace of this part of the algorithm. So it says, trace the execution of mod and div and k. That's this. Provide for positive ends, so we don't need to worry about the negative part. Show values of RD at each step of the while loop. And we'll also show the final return values as well. So all we're really doing is dividing. But notice there's lots of ways to do this. There's long division as a division algorithm. This is often called a division algorithm. And this is a whole nother algorithm all in its own right. So let's give this a try. Starting at n equals 14, and just a quick edit to make it a fast problem, k equals 18. First thing that this algorithm right here is going to do is set the values of R and D. So at step 1, we want to show the values at each step. We need to show it at this step as well. We're not proving that the pseudocode works correctly, but we're just trying to convince ourselves with a particular example. So this is not quite a proof, but maybe the next best thing before it. Set R to N, which was provided as 54 in this problem from over here. And we'll set D to 0. Now, step 2, we have to decide what will happen. Sometimes the while loop doesn't run at all. Just depends on the k value. So on step 2, we might want to do this condition check right here. R equals 54 is bigger than k, which is edited to be 18. This implies while block executed So we have a new value for R and K. R is now equal to, it'll be the old value, 54, minus the K value, 18, which is going to be, let's treat ourselves to a quick calculator on this one. 54 minus 18, we're down to 36. And all that happens with D is we increment by 1. So I'll just write in D was 0, now it's plus 1. So that's run 2 on this algorithm. When we do our next run, step 3, we have to decide if we're returning R and D, this R and that D. Before we get to that return, we're still stuck here, so we do another check. Is R still greater than or equal to K? R is now 36. 36 is greater than K, which is 18, which implies we are in fact in the while loop. We don't return anything just yet. All right, while block, just a shorthand for while block executed. That turns out to be a lot to say every single time. So now R is equal to 36 minus 18, which is 18. D increments plus 1 each and every time. So now it's 2. Then rinse and repeat ad nauseum. Well, not ad nauseum. Eventually, this is going to terminate by the while condition. But now we're at 18. And for step 4, we do a check. R is 18. while R is greater than or equal to K. I should be saying greater than or equal to each and every time, just to be specific on that condition. Well, R is greater than or equal to 18. That does pass. 18 is equal to 18, so it qualifies as greater than or equal to 18. Gets it stuck back in the while loop. R is changed. It's now 18 minus your value of K, 18 minus 18 now, set to 0. And D is now set to 3. Now we run through this whole thing again. We're still in the while loop. On 5, we do a check. R equals 0. And the condition 0 greater than or equal to K, which is 18, is false this time. So we finally get a false Boolean on the while condition. So that means on step 6, we're ready to return. We just skip down to this step. Return R. What is R set equal to? 0. Well, it should be, because 18 goes into 54 evenly. There is no remainder. R being 0 is allowed. It just couldn't be equal to K, strictly less than. So we return R equals 0. D equals 3. And that's just the number of times K actually went into 54. So that's the trace and termination of this syntax right above. Any questions at all, folks, doing that kind of weird problem for the first time? You may have done this before. Okay, well, with the conclusion there, let's come back up. Take one last quick look at this theorem. And now we can satisfy part B. It says, verify that KD plus R equals N as required by the division theorem. In other words, the division algorithm that we just traced through up here is running as intended, but only for that specific example. Again, it's not a full-on proof, but gives us great evidence that the algorithm should be correct. So let's take a look. Is N really equal to KD plus R? Well, what was N? Sorry for the scrolling. N was 54 equals K. K was 18 times D. D was the floor. We might as well highlight that. Plus the remainder. That's the value of 54 mod 18. And is 18 times 3 equal to 54 is the whole boil down of this check. Yes, it is. And so we really have KD plus R holding as true, required by the division theorem. So it's a weird algorithm. We're doing divisions by subtracting. It gets even weirder still when you realize you can do the same kind of division by subtracting in the other direction, like what we're doing over here on this block for negative N. But that's what the trace would look like for any kind of problem like that. This is the first time we've done this kind of question, so it's a good one to spend some time on. There's one just like it in the homework, and this part is a major part that's graded on. So if you did miss that part, you could lose a lot of credit, which would mean I might grade it in blue to give you an opportunity to try again on that. Well, next concept we're going to be taking a look into is congruence. Then we're going to look into actual modular arithmetic and one final function. So here's the last bit. Congruence, we have a lot to say about, just not so much in 7.2 just now, but there is just a mind-boggling amount of computer science mathematical applications to congruent mod K as a concept. Then, after dealing with congruence, here's the modular arithmetic part of the course, or this section rather. Lots of really interesting formulas for fast by hand computation. Then, turns out mod and div interacts with the greatest common factor. We're also putting down the least common multiple as a concept. This is kind of a redo of something you have done, potentially, say, in grade school and such. Good one to revisit. Because then we'll do it as an actual algorithm called the Euclidean algorithm. Our author likes to mention, this is probably mankind's oldest known, still currently used, very important algorithms, over 2,600 years old, if I recall from the reading. And it's an impressive way to calculate the greatest common divisors. Notice it uses m mod n inside of it. So we can just recall mod and div right here. In fact, that's what we'll do next time when we get to this part of the section. We'll save this algorithm. Here it is saved, and bring it back in this problem. But before we get into all those last concepts, we'll start with congruence. So for congruence, here's the way it goes. Two integers, a and b, we'll say are congruent mod k if a mod k equals b mod k. So that's the whole equation that we're trying to show. And congruent mod k is just indicated this way. So that's the notation. When you see that notation come up, think in your mind, A is congruent to B mod K. You know what, it might be better to just spell that out. Let's say that's right down here. That whole statement right there is read as A is congruent to B mod K. So using that, this is the check that we have to deal with. Being congruent to B mod K means this condition passes. So let's give it a try. I have a few just really fast problems, one that looks a little bit different with the negative there. And we're doing just ordinary modular arithmetic to check for congruence on this one. On part A, we're asking, is 73 congruent to 3 mod 5? Here's our check. Go 73. That subscript right there is telling you what the mod part is. Go 73 mod 5. And we've done a lot of modular arithmetic, so break out any tool you'd like. The author's formula that we've used today and back in chapter 2, or any kind of calculator you'd like. Because we just implemented an entire mod function, let's use this right here. Mod and div, bracket 1, is only going to give me the modulus to this. We just need to control inputs, 73 mod 5. So the order we state the modulus is the order we call the function, thankfully. And that one is just a 3. 75 mod 5 is 3. Now we check out the right-hand side of this. 3 mod 5. The remainder after division of 3 by 5, that is 3. And actually, let me do one bit of color coding there just to show where each of these parts come from. Equivalent 5 just means the mod 5 part right here. We have a match. We have 3 and 3, so this implies the congruence is true. So kind of a relaxing problem after developing weird-looking algorithms for division by subtraction. Any questions at all, folks, on that check there? Okay, let's try out another one. Is 100 congruent to 4 mod 12 is the question on this one. So it's really just two computations and then a check on outputs. Do 100. To me, this is the trickiest thing, just reminding yourself what you're doing a mod by. This is 100 mod 12. So if we do 100 mod 12, here's what the output would be. 100 mod 12 comes out as just a 4. Then finally, last one, 4 mod 12. Well, this problem seems kind of similar to the last one. If you have a value and you're doing a mod on it, but the value on the left is less than the value on the right, you just get 4 as an output immediately, just like on the last case. And just like on the last case, the outputs match up. So we can say again, the congruence is true. Hopefully they're not all true. That'd be kind of weird. So let's try out to one more in part C. Any questions at the moment, folks, with checking out these congruences? Okay, this is the weird one for sure. So let's be careful with this thing. It's weird enough that you might want an independent check, and maybe let's do -5 mod 8, two different ways, just to be really sure everything is working as intended. So first, -5 mod 8 becomes -5 minus 8 times the floor of -5/8. Let's run through this part right here. With the floor, we have -5/8 coming out as a -0.625. So the floor of that value would be a -1 altogether. So we get -5 minus 8 times -1. But now this is 8 minus 5, and we get a result of 3 altogether on that one. So let's double check that. Independent verification over here. Once I figure out where to park this. There we go. So mod and div only giving the modulus for -5 mod 8. -5 mod 8 does come out as 3 as per the algorithm. And by the author's formula, we have a match there. So it looks like we're on great track for that value 3 as output. Next thing we do is 3 mod 8. Three mod 8 is 3. It's like all my congruences came out true on this one. Sorry about that. That's a little bit weird. A congruence would have came out as false if one of those values were just different. So the congruence being true, I feel like I need to emphasize this a little bit stronger. It's just because of the trues that we're getting here. And on this one, we get another true value. So we'll say here, -5 equivalent to 3, or excuse me, congruent to 3 mod 8 is also true. Well, any last questions, folks, on verifying? Looks like all of my congruences on this one were true. I believe the homework set does have a false one, by the way. Okay. Again, this is a weird concept because our author really didn't do much with it in the book, but it's part of the toolkit that we need to develop as we run through chapter 7. So this is a concept that we'll come back to and look at a little bit more closely. Next thing we want to take a look into is properties of modular arithmetic. We have several interesting properties. Property number 1 is not necessarily saying anything too major. It's basically saying k divides k evenly for any positive integer k. So not earth-shattering on property 1, but they do get pretty interesting as you go down to the next properties. Property 2, a plus b mod k already on its own is a pretty interesting property when you really look at this. I might have suspected, if I didn't think about this too hard, the a plus b mod k should just be a mod k plus b mod k, and our job is done. That's not true. You take a mod k plus b mod k, add the results together, and then mod them by k again. That's really pretty weird. If it's a multiplication property, you do a mod k times b mod k, and then do mod k on the result of all that after multiplying. And exponentiation is just repeated multiplication. So if property 3 is true, property 4 is just a direct consequence right after. Strange properties, and they're not easy to prove as well, but our author does give some good indications on why these ought to be true. Let me know if you're curious about them. I'll be happy to come back on our next class on Tuesday and give a proof on any one of those 3 if you're curious. But really, our goal with these, as the namesake of this entire section, is just to practice doing some modular arithmetic by hand using some of these properties. Why would we want to do that? We already have an algorithm that can just rip right through it. It's more about if we're doing more and more with modular arithmetic, these properties sure help us do things by hand, but it can also lead us into other deeper properties about number theory as well. So it's like having a basic toolkit for properties of exponents, essentially. Our goal here is just to practice using them. So when you do these on the homework exercises, it's graded with this as the essential step. You really have to show the use of actually using the properties, but no harm if you actually did this as well. Let's check what our answer should be to make sure it comes out correct. 50 plus 98 mod 9. This is not our answer to the question, but this is the check. We should be getting a 4. So that's a pretty powerful tool. So now below here, we'll use property 2 and see if it really works out. 50 plus 98 mod n could be re-expressed as 50 mod n. I just keep on saying n. 50 plus 98 mod 9 is 50 mod 9 plus 98 mod 9. Add those results all together, and then mod 9 then. So let's look into this one. 9 times 5 is 45. 5 short of 50, so 50 mod 9 is just 5. 9 times 11 is 99, too far. 9 times 10 is 90, so that tells us we get 8 from 98 mod 9. So now we're at 5 plus 8 mod 9, which becomes 13 mod 9. 13 mod 9 is in fact 4. 9 goes into 13 just once with a remainder of 4. And double checking, that is exactly what we got. So doing it by brute force, no properties at all, did give us that 4. So that's how that property goes. Again, really pretty bizarre when you think about it. What would the proof of this even look like? A lot of writing out what the remainder is using the division algorithm properties, essentially taking this, solving for R, putting things in its right place, being really, really careful with your algebra, and you can deduce those sort of properties. So that's one of the major purposes of doing the division theorem in this section. It directly leads into properties of modular arithmetic. Well, that's one down. Any questions, folks, before we try part B?
I have a question.
Yeah, go ahead.
So can you just do like 50 plus 98 and then mod it by 9, or do you have to do both of them?
You could absolutely do 50 plus 98 and then just do the mod 9, absolutely. So
Okay,
that's
so
essentially,
this kind of stuff is just for like proofs if we need to like modify it somehow.
yeah, exactly. Think of this as kind of like a listing of properties of exponents that we might need later on for more difficult kind of problems or proofs like you mentioned. So yeah, it would work either way, add 98 and 50 and just do it that way. But if 50 was a variable and unknown, we might actually need this whole formula right here because we would get nowhere on that spot right there. So it becomes an important formula when one part or more parts of this are unknowns in the whole process. But thanks for that question there. Other questions at the moment? Okay, let's try it out again. This one looks like it's going to be property number 3, multiplication. 15 by 23 mod 7. Well, we could go that this is equal to 15 mod 7 times 23 mod 7 mod 7. And my answer that I gave for why we need these properties kind of fit for what was going on in part A. Honestly, I think it's easier to just really add these together, like Corbin was saying, than do the mod 9. It's interesting you can do it a different way. But if I was doing this one by scratch, just by hand, I think property 3 is actually shining pretty nicely for us. This might be more rapid than just taking this by hand, multiplying, and doing the mod 7 by hand. An emphasis on doing it by hand, right? So if I have to do this by hand, that's not too bad. 17 times 2 is 14. So that part's just a 1. 7 times 3 is 21. Times 4 is 28, so that exceeds. So times 3 is 21, a difference of 2. That tells us remainder is now 2 upon division. Mod 7 This is just 2 mod 7, it's just 2 now. So if I had to do this by hand, that's really, really rapid. So that is some good value here. Sometimes if you have to do modular arithmetic by hand, if you know these properties, this is way faster than it really looks like on face value. But let's check this out. It's good to be suspicious, so let's see if this really works. 15 times 23, mod 7, not 9, gives us an output of 2 as expected. So that's another look into the property. Honestly, property 4 is not anything new. It's just repeated multiplication, but we should still try it out just for the sake of extra practice. That's this one right here, 1000 mod 6, essentially. But if you want to do this really, really rapidly, here's how it could go. Take that power 3, put it as an exponent after you do the mod. So we're doing 10 mod 6 power 3 to match up this power. Then the output to that, we just do mod 6 again. And this is fast right here inside the group. 10 mod 6 is just 4. So this is now 4 power 3 mod 6. 4 power 3 is 64. But if we're taking mod 6, 6 by 10 is 60, excess or remainder is 4. That means we're done right at that step. 10 power 3 mod 6, by breaking it through this property right here, gives us directly 4 altogether. If I had to do 1000 mod 6 by hand, that would have probably taken a little bit longer. But if it's all the same and we just want an answer, this is really the fastest thing, certainly. If 10 was a variable, say a or x, and we need to do something with this process in a larger context of a problem, that's when this really shines. Again, like Corbin was mentioning, if it's a part of a proof, we really need this extra structure. But here's our next check. 1000, 10 power 3, mod 6. Gives us a 4 as expected, so it tells us properties looks like they're working through these examples we practiced. So that's where a lot of this stuff is going, getting more familiar with modular arithmetic. Congruence, modular congruence as well is going to be a big thing that comes back in these notes. But before these notes are completely finalized, we're going to go down memory lane and think about greatest common divisor. I'm not sure what I did to this computer. Greatest common divisor and least common multiple. I've offended this computer badly. It's beeping. I don't know if you can hear this across Zoom, but in the classroom, the computer is really upset. We'll just hope it keeps on going. When we come back on Tuesday, oh, hang on, what's that? Sticky keys. I must have played something. Play a sound when modifier keys are pressed. Just turn that off. Oh no. We might have a problem on the next class, but we'll survive that. I think we're at a good stopping point though. Any last questions, folks, with where we ended on? Okay, well, this will be our stopping point. Sorry for the massive distractions at the very end of class. We're going to develop some information on least common multiples, greatest common factors, and then intersect the mod and div algorithm with the Euclidean algorithm down here and see what new interesting stuff we discover. But have a great weekend, folks. I'll see you all on next class on Monday. Got the day wrong, I think.